For the ICRA 2020 online conference, we present ARCSnake, a collaborative effort between UC San Diego and NASA's JPL. ARCSnake is an Archimedes screw-propelled reconfigurable serpentine robot. The robotic platform was developed to be a mobile robot to explore remote, complex terrain. In particular, the project's goal was to design a robot that is intended to be a transport platform for instrumentation and capable of exploring small tortuous chasms of Enceladus in search of extant life forms. The inspiration for the Archimedes screw design used as the platform's active skin comes from the days of ancient Egypt. The design was used to lift water from the Nile and possibly used to irrigate the Hanging Gardens of Babylon. Archimedes documented these designs when visiting Greece and was incorrectly attributed as the inventor of the screw mechanism. The first screw-propelled vehicle, known as amphirols, was designed in 1868 and used for moving in snow and water. Similar to this vehicle, our robotic design will utilize the Archimedes screw for locomotion. The design also incorporates a U-joint to reconfigure the robot body in constrained environments. Finally, it is designed with modularity in mind and consists of 4 modules and a head unit. There are 3 major components to ARCSnake's design. The first is the mechanical portion, which covers the Archimedes screw shell and U-joint. The second is the electronic portion, which includes the onboard embedded system and sensors. Lastly is the software design, which covers the communication channels and control architecture. The Archimedes screw module is the active skin in the design. The outer screw shell is coupled to the inner shell through a bearing. The inner shell houses all the electronics and the motor driving the Archimedes screw. The Archimedes screw was designed with a 22 degrees helix angle for maximum pull and minimal slippage. It can also reach 100 RPM, which results in a speed of 0.23 meters per second. Lastly, it has an output torque of 1.6 Newton-meter continuous and 2 Newton-meter peak. A U-joint is placed between each Archimedes screw module to reconfigure the shape of the robot. We chose to use a pitch-yaw configuration for the U-joint since it avoids the gimbal lock when nearing the straight configuration. This is since our snake should operate in the near straight configuration when exploring through tight chasms. A timing belt provides the final gear reduction for the U-joint due to its low backlash, high load rating, and high stiffness. The U-joint is capable of moving at 87 RPM with an output torque of 2.1 Newton-meters continuous and 2.7 Newton-meters peak. This is enough power to lift an unsupported attached Archimedes screw module. Magnetic encoders are also used in the design to provide absolute positioning of the U-joint. The electronics are designed with modularity in mind and housed in the inner shell of the Archimedes screw module. The onboard embedded system used in our robotic platform is the BeagleBone Black. Each module has a self-contained embedded system, network switch, and IMU for scalability. Buck boost regulators are used on the custom-designed PCB to regulate the voltages supplied to all the onboard electronics. These regulators provide robustness against voltage disturbances due to the sags from long cable runs. The 3 onboard motor drivers drive the Archimedes screw motors and U-joint motors. There are multiple built-in safeties from the electronics such as temperature protection, voltage and current protections, and range of motion limits. The software communication and control architecture was also designed with modularity in mind. The remote desktop runs a ROS control node and ROS's visualizer RViz. The desktop's ROS control code communicates via network with the onboard control code. The onboard control code reads from the IMU and encoder sensors. The encoder readings are then used as feedback to a PID controller, which regulates the motor's position. The motor control code is scaled to all 3 of the onboard motors per module. The onboard control code is ran on all modules and daisy-chained via the Ethernet network switches. Finally, there is a camera which is attached to the head of the snake and communicates via Wi-Fi to the remote desktop. Validation of the system was conducted through various laboratory experiments. These include the ability to regulate the U-joint position across varying input voltages to the modules, torque transparency for force control of the U-joint, thermal performance of electronics under heavy load, finally transitioning between configurations for locomotion. Here the snake is transitioning from a straight configuration to a M configuration, to a square configuration, and lastly back to a straight configuration. We also experiment with locomotion in the M shape and square configurations. These locomotion results show promise in ARCSnake's ability to traverse through a large variety of terrains due to the many possible configurations for locomotion it can have. For future work, we are investigating more configurations for locomotion and their performance in different terrain. Thank you for listening to our presentation, and please scan the QR code to visit our website.